temperature. For example, I have here the water phase diagram. At atmospheric pressure, it can tell us where are the critical temperature at zero Celsius. Yeah, sorry, 0 Celsius and 100 Celsius. Here we can see that is phase in transition from solid to liquid and liquid to gas. This line right here is called first order phase transition. The first order phase transition are characterized because there is a discontinuity in the first derivative of the Gibbs energy, and also because it has latent heat, meaning that we can have two states of matter at the same time. For example, when boiling water, you can have water and also steam coming out, and that is the first order phase transition. But at high energies and high temperatures and also high pressure, we have more interesting things happening here. What will it look like at this point right here? Anyone knows? Well, this is called the crossover region. The crossover region is characterized because it's only one state of matter. It is not a liquid, it is not a gas, it is the crossover region. And also we have the critical point. So that's introduces us to the quark-gluon plasma. Quark-gluon plasma is a different state of matter where the hadronic matter is deconfined, and because quarks and gluons are confined inside the nucleus, and this state of matter is happening at low temperatures and low baryonic chemical potential. On the other hand, at high temperatures, when we increase temperature or when we increase the baryonic chemical potential, we can have quark-gluon plasma, where the quarks and gluons are deconfined from the nucleus, and it can move freely in the volume. We can see here that the critical point is right here. Well, this is an approximation. We are trying to find the critical point. At the beginning, we have a crossover transition, and then the first order phase transition. That is also speculative. So the critical point, it is important because it can tell us where the crossover region ends and start the first order phase transition, or vice versa. It is a key feature in the QCD phase diagram because it can unify experimental and theoretical data. And there has been running different experiments to find it in the Relativistic Heavy Ion Collider, the beam energy scan, and also the STAR experiment. It is important because right after the Big Bang, for microseconds, less than microseconds, all the matter was condensed in a single point, and also it was very hot and dense, that the quark-gluon plasma phase was the state of matter in all the universe. For generating quark-gluon plasma, it has to be created at higher temperatures and high density, so we can only do it with colliders, particle colliders. As part of my research, I went to the Relativistic Heavy Ion Collider in the Brookhaven National Lab, and I visited the star detector, and I saw a couple of simulations that you have to collide two particles at almost the velocity, almost the speed of light, to create this state of matter, so condensed and so hot. And also, it's a state of matter that it's only lasts it lasts less than 1 microsecond. It's very, very hard. After that, the matter starts to cool down, and then you have again the hadronization phase. An equation of the state. An equation of the state is important because it tells us how relates. It's a function that relates different thermodynamic variables. For example, we we have here the equation for the van der Waals. We have the van der Waals equation that relates the pressure, the volume, the number of moles, the gas constant, and the temperature. Here we can see how it will look like in a three-dimensional space: pressure, volume, and temperature. And this is the equation, the van der Waals equation. The critical point, we can find it here, where this is a first order phase transition right here, and this is the critical point. After this, we have a crossover region. That's why there are different frameworks to try to construct this equation of state. One of them is the Ising model, Quantum Chromodynamics, where we can, the Ising model shares the same universality class than the QCD. That's why we can use it to describe the QCD phenomenon. And also here is an equation of a state of the quark-gluon plasma phase of the equation of a state. And here we can find where is the critical point. And also here we can see that there's a lot of perturbations. One of the characteristics of the critical point is that we have perturbations in the susceptibilities here around the critical point. I'm sorry. So, as part of my research, I study and run simulations of these two different frameworks. I have the four-dimensional Taylor expansion model and the Ising two-dimensional Taylor expansion model. For the input, I use different parameters in temperature, not going beyond 500 MeV, and I use baryonic chemical potential, electronic chemical potential, strangeness chemical potential. For these simulations, we set the electric chemical potential to 0 and the strangeness chemical potential to a fixed value. And then we can have a three-dimensional space where we can run equations of a state like slices in the strangeness chemical potential axis. As an output, I get temperature, baryonic chemical potential, electric chemical potential, strangeness, mean pressure, mean entropy, and mean energy density. These ones are used to physically validate the equations of the state, because the frameworks can give us invalid equations of the state. I'm going to talk about this. And then I have the Ising model, two-dimensional Taylor expansion models. This framework only uses temperature going less than 800 MeV and baryonic chemical potential. Also, the four-dimensional Texas model doesn't include the critical point. The two-dimensional Taylor expansion model does include it, because we have as the Ising model that it starts with a first order phase transition, has a critical point, and then a crossover region. Then we can map this and convert it to the QCD equation of state, where we can find where here is the critical point. And also it gives me the same output, the thermodynamic variable, so we can validate these equations of the state. As part of my research, I also use the supercomputer commuter. I access it via SSH connection, and we use it to generate massively generate equation of state of the four-dimensional Texas framework. This is the workflow. This is the workflow of my pipeline, and here we can see how we can generate massively equations of a state, and then here is the validation of my equation of a state. To physically validate the equation of the state, it has to be causal and stable, meaning that it has the speed of the sound, it has to be between 0 and 1. And for stability, these to respect the relativity. And for stability, the specific heat has to be greater than 0, and the susceptibilities has to be greater than 0. And thank you so much.